Good morning, everyone. Today we will continue with our topic for this week. We have looked at the conductors and we have seen how to apply Gauss's law on several spherical conductors with excess charges on the sphere and with the existence of a point charge right at the center of a spherical conductor. Today we will look at Gauss's law in dielectric material, and we'll also look at the dipole and how to calculate the dipole moment and the torque of a dipole in the existence of a uniform electric field. We will also look at dipole in the existence of a non-uniform electric field. Dielectric materials, the only example we have seen so far was the free space. And we said in the free space, the Coulomb's constant, we defined it as K equals to 1 over 4 pi epsilon naught. And we said that the epsilon naught is the permittivity of the free space. And this is for the free space. The free space is our reference when it comes to the permittivity. Now, if we have other insulators than the free space, then we will need to introduce what is called the dielectric constant. The dielectric constant is given as a capital K, and in this case, the Coulomb's constant with the existence of an insulator that has a dielectric constant would be the following: small letter k equals 1 over 4 pi k capital epsilon naught. So for the case of a free space, if this is my general expression, then for the case of the free space, this is 1, which is the dielectric constant for the free space is 1. Now, what does this mean? This means that there are other materials that are considered insulators and they have a dielectric constant and it varies from one to another. So the free space is one. We can, for example, see that the dielectric constant for the water is 80.4. The dielectric constant for the glass between 5 and 10. Also, what else? Teflon, the dielectric constant for the Teflon is 2.1. So those are some dielectric constants for uh, some materials. In this case, if I am to write the uh, Coulomb's constant for the Teflon, it will be 1 over 4 pi k epsilon naught. And in this case, k is 1 over 4 pi times 2.1 times 8.85 10 to the power minus 12. Or what I can say that if I am to write it here, then k would be 9 to the power 9 divided by 2.1. So you can also use this expression, which basically make it easier for you. Take the k, the Coulomb's constant for the free space, divided by the dielectric constant. You get the new Coulomb's constant for the material that is considered an insulator. Now we'll look at Gauss's law on insulators. If we have an excess charge on this insulator and those charges are distributed uniformly inside this insulator, in this case, we will use the charge density that we have seen earlier, rho, which is Coulomb per. And in this case, we can apply Gauss's law as following. So let's do this. What we have here is this insulator with a radius capital R and a positive charge. So the first thing we need to do is to draw this spherical insulator where we have charges distributed within the volume uniformly everywhere. We have the radius r for this insulator, and we also know the charge density. So we have here charges distributed within this volume. This volume is a sphere. We know that the volume for the sphere is 4 over 3 pi r cubed. This is the volume for the sphere. Now, what's going to happen is the following. If you recall, when we wrote Gauss's equation for that says the closed form integral of the electric field over that surface equals to Q enclosed divided by epsilon. I will say epsilon now because this is the general case. It could be an insulator that has a dielectric constant, not necessarily free space. So leave it as an epsilon. Now, the thing that we have to pay attention to here is, as we will see, the Q enclosed. Now, when we dealt with conductors, charges were either at the surface or and as a point charge in the middle of the cavity. Here it is a bit different. We will see why is it different. So let's draw the Gaussian, my Gaussian surface inside. So I will be dealing, as I said, with two regions. Region 1 inside the insulator, region 2 outside the insulator. So if I take my Gaussian surface to be this one for region number 1, so this is small, this is small letter r, that's my variable. This is the radius of my Gaussian, so this is my Gaussian surface, which is a sphere in this case. This Gaussian surface is a sphere. Now, something you need to pay attention to, and I will keep it in a different color here also, is this a Q enclosed. Notice that the Q enclosed is not defined as either all enclosed or all are outside. No, I have charges everywhere distributed uniformly based on this volume charge density, which means as long as this Gaussian surface is sweeping, the surface is sweeping means the volume is increasing within this closed surface, which means it will capture or it will enclose more charges. So now, if I say that this Q enclosed, it's going to be a function of this R for my Gaussian surface. This would reflect the amount of charges enclosed within this Gaussian surface. So this Gaussian surface basically is defining a volume. Now the charge enclosed is basically a function of this radius. So here, this Q enclosed now, I will replace it with the following. So the charge enclosed here would be rho times the volume of the Gaussian surface. And what's this volume of the Gaussian surface? It is 4 over 3 pi r small letter cubed divided by epsilon. So this is my enclosed charge. So this enclosed charge is basically defined by this Gaussian surface. And here, similar to what we have done in last lecture, we can see that this electric field is in parallel with the differential element, and this is the dot product now. Both of them are r hat. So this is going to be, this is ER r hat dot dA r hat, and now this is going to give me ER dA equals to rho 4 over 3 pi r cubed over epsilon. Now ER is constant, then can go outside, and now this is going to end with ER, and now the integral, the closed surface integral of dA is going to give me the surface of this Gaussian. So now this is going to be 4 pi r squared equals to rho 4 over 3 pi r cubed over epsilon. Now, as long as we are inside in region number 1, so here we are region number 1, this Gaussian surface is capturing, the one that's capturing the charges. And as long as this Gaussian surface is sweeping inside, this R takes, this R here in this region goes from 0 to capital R. This is region number 1. Then the charge enclosed is a function of this R. It's not constant. It is a function of this R. That's why we kept it as a small letter here. Now R squared will cancel with the cubed here. Pi will also cancel. 4 will cancel, and I will end up with ER equals to rho R over 3 epsilon. Rho R over 3 epsilon. This is the electric field for region number 1. Now if I am to draw this along R, then I have here R capital. So I can see, let me make this one. Here. Then I can see that R, when R goes from 0 to capital R, I have a linear function here. I have this linear function. The maximum would be right at R. Why? Because right at R, my Gaussian surface will be capturing all the charges within this insulator. And then what happens after after we get to region number 2? Let's look at what's going to happen for region number 2 now. For R greater than capital R, I have the same ER 4 pi R squared. However, the Q enclosed now, when I am outside, so let me draw the Gaussian, the new Gaussian surface for that region. you can see that in region number 2, I am enclosing all the charges, the maximum charges, because I'm starting from R and going increasing. So I am already capturing all the volume charges. So the Q enclosed here, my Q enclosed is this rho times 4 over 3 pi r cubed. Why did I take the r capital here? Because r capital here defines all the charges. I already enclosed all the charges. From r and going further, in this region number 2, I already enclosed all the charges. So this is going to be the capital R divided by epsilon. Then rearranging. Here I cannot cancel the R. 4 is going to cancel. Pi is going to cancel. So my electric field now, ER, becomes rho R cubed over 3 epsilon R squared. Now, if you want to put this one in vector, then it will be rho R cubed divided by 3 epsilon R squared R hat. Now, if you want to draw this, you will see that this one will be decaying as an inverse proportional to the R squared. So this one is going to do like this until it becomes 0 at infinity. So that's the difference. Here, again, what was this? Maximum rho R. It happens when this little r equals to R. I get the maximum divided by 3 epsilon. So this is the electric field right here, and this is where the electric field becomes maximum. So again, if you substitute this small letter r with capital R to calculate the electric field, you will get the same value as here. Okay. So here in this example, we left it as epsilon naught. You can, assuming that this is a free space, in general case, it would be epsilon. Dipoles and insulators. If you bring a charged rod closer to insulator surface, we have seen that this charged rod is going to polarize this insulator, causing the charges to be right at the surface to be polarized, such that the positive will be turning toward the negative charges, while the negative ones will be pointing away. And this happens when I have an insulator that has polar molecules. In that case, those atoms inside this insulator will be easily polarized. And as you can see, charges will be ionized right at the region that is closer to this charged rod. Now, this happens due to the external charge, as we have seen. What's going to happen that those atoms are going to be polarized. Negative charges will be displaced, causing the atom itself to be ionized, and in this case, they will be polarized and pointing toward this charge, such that if this is a positive charge, the negative would be pointing to it, the positive would be pointing the other way around. And this is because of this external charge that is creating an external electric field, and this electric field is inducing forces on those charges, causing them to rotate in this direction, as we will see in more details in the coming slides. So that's what we were talking about. If you have an external charge, then any atom that is polar in nature can be polarized such that those cloud of charges will be displaced and toward going toward the positive, the opposite charge, while the other one is trying to move away due to the forces, of course, exerted by the existence of this external charge that is creating an external force. And we have seen this before, and we have dealt with electric forces before. Now, when those atoms get polarized, they create what are called dipoles. So the dipole in general is uh, two charges that are equal in magnitude, opposite in their sign, and they have a very small distance in between. Now we want to introduce what's called the dipole moment. This dipole moment, small letter p, it's a vector, and it is pointing from the negative charge toward the positive charge. So always remember that the dipole moment is pointing from the negative charge toward the positive charge, such that the displacement vector S vector is also pointing from the negative charge toward the positive charge, while the Q here is a magnitude of either of those two charges. So we define what's called the dipole moment, and this dipole moment is a vector, and it points from the negative charge toward the positive charge. So this dipole moment, as we will see, if we put this dipole inside a uniform electric field, this uniform electric field, they have constant magnitude and they're all in the same direction. So what's going to happen in this case, if this electric field is uniform, what's going to happen to this dipole? In this case, as we have seen earlier, charges, positive charges, will be attracted such that the force exerted on it will be parallel to the electric field. Negative charges will be anti-parallel to the electric field, and this is going to cause this dipole to rotate this way to be aligned such that the dipole moment that we have introduced earlier, pointing from the negative charge toward the positive charge, will be parallel to the electric field. So one of the specs for those dipoles, that they always turn such that their dipole moment is pointing parallel to the electric field. So in this case, if this dipole was placed in this uniform electric field and it was released from rest, what would you expect it to do? This dipole moment, based on the forces applied on it that we have understood earlier, will tend to rotate such that this dipole moment now is parallel to the electric field. So in this case, it will rotate counterclockwise around its center of mass till it completely align with the electric field. Now, this dipole is not going to move left or right. Why? Because the net force applied on this dipole is zero. Why? Because those charges, they have the same magnitude, and the electric field is a uniform electric field. So the force here that I will call F plus will be equal and opposite to the force that I'm calling here F minus. Okay, so we understood what the forces were doing we understood that the dipole moment will need to align with the electric field, with this uniform electric field. Now introduce what's called the torque that you have seen earlier. The torque here is the product between the displacement vector. Remember the displacement vector pointing from the negative toward the positive, S, cross the force F. So here in this case, if we define the center of the mass here, then I have here force F over 2. This one, the F minus would be F over 2, or those are two equal in magnitude. So this one would be because of this line that has a split into now two halves. Then I have S over 2 times F times sine phi. And why sine if this is the phi? Because this is the component that is responsible for the torque. So this component is F sine phi for both cases, for either the positive or the negative. Let me redraw that. So for both cases, if this is the center of the mass, then this is the component that is responsible for the torque, and that's why this is F plus sine phi, and here this is half of the S, so this is S over 2. This is S over 2 between the charge and the center of the mass. So I have here S over 2 times F plus sine phi, which is this force, S over 2 times S minus sine phi, which is this component, right? And this one is the other component here. Then the total would be S F sine phi, and I know F is Q E. So the torque would be given as SF sine phi or SQE sine phi. So tau is SF sine phi and F as QE, then SQE sine phi, and SQ is P, the dipole moment that we have introduced earlier. So now we can rewrite the torque in terms of the electric field and the dipole moment. Why? Because we have said that there is uh, a relationship between the dipole moment and the electric field. The dipole moment always tend to align with the electric field such that it becomes parallel with the electric field. So the torque is the cross product between the dipole moment and the electric field, and it's always trying to align itself with the electric field. So this is what's happening in a uniform electric field. It's always want to align itself. So here, this is the dipole moment going from the negative to the positive. So in this case, the dipole moment would like to flip itself in order to align itself with the electric field. In both cases, this dipole has a net force of 0. Why? Because the electric field is uniform. The force exerted on the the positive charge, equals in magnitude to the force exerted on the negative charge. And as you can see, they are in opposite directions, but the net force is 0, which means this dipole is not going to move. This dipole is only going to rotate, such that the dipole moment becomes parallel with the electric field, And at this location, when they align the dipole moment with the electric field, the electric potential energy would be minimal. This is the lowest value of the electric potential energy. Okay, so if that's the lowest value for the electric potential energy, when they align, when the dipole moment align with the electric field, so here in this case, the dipole moment will the dipole will flip such that the dipole moment is aligning with the electric potential energy. In this case, the electric potential energy would be minus dipole moment dot the electric field. Why? Because when this dipole moment is anti-parallel with the electric field, this where I have the maximum electric potential energy. And again, if you do the math here, you will get the minus P magnitude E magnitude, and the angle, as you can see, is 180 degrees. Then this is cosine 180 degrees, and in this case U becomes positive PE. So if you compare now those two states where the dipole moment is parallel, I have U equals to minus PE. This is the electric potential energy. When I have the dipole moment anti-parallel, I have the electric potential energy being positive. So if this is my electric field, uniform electric field, and I have a dipole moment that is pointing, aligning, we said that this position when it's aligned, when it's parallel, has the lowest electric potential energy. So if I call this one U1, then U1 would be minus P dot E, and since they are parallel, then the cosine 0 is 1, and this is my electric potential energy. This is 1. Now, if I have electric dipole moment that is anti-parallel, so let me call this one P2, then in this case, I have here U2 equals to minus, again, P dot E. However, P magnitude cosine, the angle now between the electric field and my dipole moment is 180 degrees, and that's why this becomes PE. Notice that electric potential energy at position 2 is greater than the electric potential. This is the maximum actually, while U1 is the minimum. So that's why if you release this dipole from rest, it will flip such that it is always aligning with the electric field, which means it is going from the high electric potential energy toward the lowest potential electric potential energy, and this is in the existence of a uniform electric field. Now, what happens if this electric field was non-uniform due to a point of charge? As you can see, uh, once you are far from this charge, if you go further away, then the electric field becomes weaker, and as a result, the induced force on any charges becomes less. So if I have a dipole in the existence of a non-uniform electric field, and this negative charge is closer to my positive charge than this one, so this dipole, as you can see, it's rotated already. The negative charge is closer to my capital Q than this small positive charge. In this case, the force exerted on the negative charge in magnitude will be greater than the force exerted on the positive charge in magnitude. And in this case, the dipole will align itself. Again, the dipole moment will align itself such that it is in the parallel to the electric field. However, the sigma f is not zero this time, which means that the dipole will start drifting and moving toward the positive charge in all cases. Why? Because the force here is greater than the force here. So I have a net force going toward the charge that is generating this electric field. So that's what's happening. In both cases, it will be attracted toward the charge. Either if the charge generating the electric field was negative, and in this case, even if the charge was positive. Why? Because if it's negative, then the positive polar side of the dipole will be attracted. The force exerted on here greater than the force exerted on here. If the charge that is generating the electric field is positive, the dipole will also be attracted because the negative charge here will have an attractive force, and this attractive force here is greater than the one on the positive side. So in both cases, either the charge that is generating the electric field was positive or negative, the dipole will be attracted, aligned, aligned and attracted. Now look at the electric field here for the positive charge. Let's look at the electric field for the positive charge. The electric field is pointing away, right? Away. Look at the dipole. Look at the dipole moment. Dipole moment is aligning with the electric field. Now look at the electric field here, pointing toward the negative charge, right? Look at the dipole moment. Dipole moment is also aligning such that it is parallel with the electric field. So it's always parallel with the electric field. If it's a positive charge, electric field pointing away, it will be parallel pointing away. If it's a negative charge, electric field pointing toward that negative charge, then the dipole moment will be pointing toward the negative charge as well. And now this reaches the end of our material for this week. I would like to remind you here with some important points, a summary of what we have seen so far. And in addition to what we have seen and what we have mentioned earlier, we also have seen that positive charges, they move in the direction of the field lines. Negative charges, they move against the field lines. Electrostatic force pushes charges in the direction of lower potential energy. Positive charge moves to lower electric potential, and negative charge moves to higher electric potentials. We have two exam type questions here. I would like you to think about it, and we will discuss them later on in our live session.